Good afternoon, I think, yes. My name is, well, first of all, thank you for coming to this session. My name is Cesar Saavedra, and I'm with Red Hat, and this is Thomas.
Yeah, my name is Thomas Qvarnström, and I'm also with Red Hat since 11 years, and I work with technical marketing. So,
and our emails are here. Please, I think you're going to get a copy of the presentation, but you can feel free to take a picture of that, and also our Twitter handles there. So this presentation is about path to cloud native app dev, 8 steps or recommendations to cloud native application development. So let's get started. So first I'd like to go over the evolution of what I call cloud application services or frameworks. So the concept of off-premise computing is nothing new. It's been around since the 70s. Back then, we had what we call the value-added networks that usually handled EDI processing. And this was basically companies that had their own data centers and corporations and customers would hire them to do the EDI processing for them. Then in the 90s, the concept of co-location became popular. And this is obviously the idea that instead of having your own data center, you would basically rent someone else's a part of someone else's data center to run your workloads. Amazon was founded in 1994. Compaq coined the term cloud computing in 1996. Then RosettaNet and protocols that exploited the internet came into the picture in the late 90s. RosettaNet being a protocol used mainly by manufacturing companies to process transactions across different partners companies. Salesforce, the first successful SaaS corporation, was launched in 1999. The Manifesto for Agile Software came into the picture in 2001. EC2 from Amazon came into the market in 2006. And Netflix streaming, movie streaming, happened in 2007. The same year that the iPhone was introduced, and everybody basically became had a digital presence on the internet. Java EE6 happened in 2009, the same year that Uber was founded. Netflix coined the term cloud native in 2010. Dropwizard, if you heard of the concept of fat jars, they came up with that concept in 2011. Have you heard of the 12-factor app manifesto? That is pretty popular. That Heroku put that together in 2011. Microservices, as well as the definition of them, came between 2012 and 2014. So did Spring Boot in 2014. Docker was 2013. Kubernetes 2014, and containers were popularized in recent years. And now we live in a world where containers, cloud, microservices are basically, the direction that every corporation is trying to go into. And why is everybody rushing to adopt these frameworks and services and the cloud? Is because of what we call digital economy. I know this is a term that has been used for the last few years a lot, but there is a reason why companies are rushing to get on the digital economy bandwagon, and the reason is that there has been studies that actually show that if you are digital, you are better off as a company. For example, you will be more profitable, 26%. You will have a higher market valuation of 12%, and your revenues will be higher at around 9% higher. But companies and corporations have this challenge that they've been running their businesses successfully for so many years, or for the last decade or so. And they have lots of existing IT processes in place already. However, to take advantage of these new concepts like microservices, the cloud, containers, that give them greater agility to get to the market first or faster, they need to be able to adapt what they have already in place. So that's a challenge that companies are seeing. So that's where cloud native app dev comes into the picture, right? It kind of changes the way you develop software. And in cloud native, you have these two concepts. You guys understand the concept of yin and yang, where two parts, when they are together, they will actually, work better than separately. And they complement each other. And in cloud native app dev, we have the concept of infrastructure services. These are the services that have to do with operational things like the building and the delivery of the application. The main once the application is in production, you know, how to update it, how to patch it. All these are infrastructure services. But then there is the concept of application services, which is what helps you develop faster, develop business logic faster. Okay, so this is the concept of you know, libraries, frameworks, things like you know, Spring or Java EE. You know, these are frameworks. These are application services. Also, there was a research study done in August of this year by GatePoint Research, and it's called the Pulse Report. And this just confirms what you know, this idea of speeding up or having application services and operational services. You know, if you look at the results here, 75% of the respondents, they wanted that the issue that the concerns that they had were related to the speed with which we can add and modify applications, and this talks to right to the application services. And 57%, they said that the speed with which we can change our operational process, and that talks to the operational services that I mentioned. So what is cloud native app dev? So it's a modern approach to building and running applications that exploit the cloud computing model, and based on these 4 key tenets. For architecture, you have a service-based architecture, you have an API-driven communication, you use containers for infrastructure, and for process you use DevOps. And if you look at these 4 squares or quadrants, the ones on to the left, the architecture and communications related, are development concerns. Okay, this is what's going to help you develop business logic. And the ones on the right, the infrastructure and process, these are the delivery and deployment related concerns. Okay. So some differences between, you know, the way we used to develop code, and many companies still do, and versus cloud native app dev are listed here on this table. And I just quickly mention a couple. You can read this at your own pace later on. But you know, the focus when it comes to traditional is longevity and stability, whereas with cloud native is speed to market. Delivery cycles are long in traditional and short and continuous in cloud native. The architecture is tightly coupled and monolithic in traditional app dev, whereas in cloud native is loosely coupled service-based and API-based communication, which were 2 of the tenets that we covered in the previous slide. Infrastructure in traditional is server-centric, and whereas in cloud native, you know, it's container-centric. You know, it's on-demand capacity, it scales fast up and down. So now let's jump into quickly to the 8 recommendations on steps. Please don't take these steps as in the order that they are listed. They are not listed in any specific order. You can start with whichever step you want. Okay. So the first one is evolve a DevOps culture and practices. So this is take advantage of the new technology, you know, and the faster approaches and tighter collaboration. These are the results from a survey, developer survey done at the end of last year by IDC. And in which 51% of the respondents said that they had already adopted DevOps. However, out of those, only 20% were using DevOps for 10 and 40% of the applications that they had. So there is still room to grow in organizations to continue adopting DevOps. And why DevOps? Because these are the benefits, some of the benefits you get by using DevOps. You know, it encourages experimentation. Fast failure, you know, I'm sure you've heard of the concept of fail fast. You know, it catalyzes innovation, it boosts trust and cooperation across teams. You build prototypes fast, and you adopt agile workflows. The second step or recommendation is to speed up existing applications. So as I mentioned before, many corporations have monoliths that are running their businesses. So the idea is to migrate those to a container-based platform, and this is showing this picture right here. You know, a typical Java EE application, how it's being moved to a container-based platform like OpenShift, and just by moving your monolith to a container-based platform will accelerate remember the 4 quadrants, the 2 of them were related to delivery and deployment. Just by moving your monolith to a container-based platform will address those 2 quadrants on the right, and you will gain benefits from that. This is sort of the next step. Once you moved your monolith to a container-based platform, that may be enough. You can stop there. But however, if you want to continue breaking up your monolith, you can start doing so. And in this picture, you know what's showing here is that the monolith has two of the bounded context or specific services or microservices within the monolith have been split into 2 separate microservices. One in Spring Boot and the other one in Thorntail. I forgot to update that. Instead of Wildfly Swarm, it should say Thorntail. And then you can actually front them with a gateway or even maybe an API management solution like 3Scale. This is actually called the strangulation pattern when you start breaking up the monolith. And the last step could be, you know, if you decide to do so, you can actually break up your monolith in microservices, and at the end, you can retire your monolith. You won't need it anymore. Once you have we'll have rewritten it in microservices. Step number 3 is use application services. So what are application services? I was talking about speeding up business logic development earlier. So for this, you know, there is no need to recreate the wheel, right? So if you need to put, you know, cache memory and cache data in memory, for example, you can use an in-memory data grid. If you want to do some data virtualization, you have data spread out across different data sources, like different databases. You can, for example, use data virtualization product or offering or open source project to handle that situation. If you want to do messaging, instead of writing your own messaging solution, you can again leverage what's already existing in you know, as an open source project or a product. Serverless is another option, but the point here is that there are many tools at your disposal that you can use to speed up the creation of business logic. You don't have to recreate the wheel. Number 4 is choose the right tool for the right task. So I would like to show you there are 2 interesting points right here, and I don't know if you can read all the way in the back, but there were 2 surveys done. One was done at the beginning of this year in April, but by the Eclipse Foundation, by the way. And the respondents, most of the respondents said that most applications today are being constructed by teams of developers employing multiple languages. The days of shops being a .NET shop or a Java shop or a Solaris shop, that's long gone. Now businesses are using multiple solutions and multiple runtimes, you know, in their applications. Same thing. There was a survey that we run at the end of last year, and among Red Hat customers, 80% of the respondents said that they were using or considering multiple technologies for microservices. On the right side, you see microservices technologies that you can use. If you want to use reactive programming, you can use Vertex, for example. It's an Eclipse project. You can use Go. You can use Python. You know, you can use Jakarta E or Java E, MicroProfile, Spring Boot. These are all different runtimes that people are now using. So now I'm going to switch to Thomas. He's going to show you a quick demo of some of these runtimes.
Yeah. So we thought we were going to show a bit of examples for when choosing the right tool for the right task is important, and why it's important to have a tool set of different toolboxes when deploying cloud native application development. So in this demo, we're going to use a fairly simple web shop application which displays different products, and one of the important things here is it also displays the number of products we have in inventory. The architecture for that is quite simple. We're doing in a microservices architecture where we have basically a browser accessing the web page, and the web page will then call the gateway and ask for the number of catalogs we have, and ask for the products we have in the catalog. That's one request going down from the browser down to the gateway. But then the gateway also needs to ask the inventory service for all these inventory data, how much inventory data we have for every product. And since we have currently 8 products in our product catalog, that means we have to call the inventory 8 times. So that's the core of the demo. And with that, I'm going to switch over to the demo. And here you can see the application running, by the way. And oops, sorry, wrong button. And we can see that it responds quite simple. And by the way, that pattern that I showed you is a microservices pattern called microservices gateway, where we avoid having multiple calls from the client down and instead aggregating multiple clients in a gateway, multiple calls in a gateway. But doing distributed computing like this could be hard, and doing distributed architectures could be hard. And one thing that a developer might not realize is that the inventory service might be having bad performance. And that will of course affect the response time even worse in the gateway. So in this example, what I've done is I have 2 parallel deployments here. Now I'm currently using actually a Spring Boot version, but it doesn't have to be Spring. It could be any type of servlet-based runtime out there. We have Thorntail, other microprotocol, etc., that are non-reactive. And we'll see what happens when we do that. And actually, let's first see what I'm also using a distributed tracing system called Jaeger here. So with Jaeger, I can find traces. I can find a trace of how that call stack hierarchy looks like between the different services. So the first thing we see here is we see a call to the gateway service, and the gateway service. Let me see there. And the gateway service will then call the catalog service. And the catalog service here, we can see is responding very quickly. It's responding in 1 point. I don't know if you can see that. I'll see if I can zoom in here. It's responding in 1.6 milliseconds, retrieving the catalog products. And then for every product, the gateway is then calling out to the inventory service. And as you can see, that is happening in serial here. So since I actually put in a delay for my inventory service to show this use case, and this delay is 100 milliseconds, so we can see that every call to the inventory service is taking about 100 milliseconds here. And that's why we get this nice staircase look in the logs. But that's actually a bad thing. If our inventory service were and we can see the total duration for this call is actually 850 milliseconds. And if that duration was even more, that would even stack up even higher. So we will quickly get bad performance out of that. So let's actually see what happens if we put some load on that system. So I'm going to run, here we go. I'm going to make that a bit bigger. So you can see that. That doesn't make it bigger, does it? Is that a bit bigger? Not really. So let's see it like that. Let's do clear. Oh. See if that looks better. So what I'm going to do, I'm not going to do 50 clients in the beginning. I'm going to call this service with 10 clients doing 10 calls each. And the rest is just basically a way for me to find out the actual URL I'm going to call. So I'm going to put that into to that Spring instance. And immediately we can see that during a bit of load, what actually happens is that this Spring service starts to respond with 500 server error. Why is that? Well, that's because every incoming request will actually be assigned its own thread in the servlet container, and that thread in terms will then actually use 8 different connections to call to the other service, to the inventory service. So eventually what happens here is that because of that, and because we're doing it that way, what will happen is that we will run out of threads in the servlet container that doing external calls, and we're actually running out of threads because we're doing blocking calls here. So that's why we get 500 server errors for some of the actual requests going through here. That's obviously not a good state where we want to be. Let's just check some data. First, we have a transaction rate of about 10 transactions per second here. We have 90 successful transactions out of 100 calls. So 10%, then 90% availability for this service. So what I'm going to do now, I mentioned before that I had two services. I have two similar services that does exactly the same thing, but the other one, let me show you that here and go back here. And so we can see that we have one gateway here called Gateway Spring, and we have one called Gateway Vertex. Oh, sorry. The Vertex one is a reactive platform, and reactive platform means that it has possibilities to do non-blocking calls instead of doing blocking calls. So we're going to apply that pattern now and see what happens if we're going to use a reactive platform as a microservices gateway instead. So let's zoom out here again. And for that, I'm using Istio to route traffic here, so I need to edit the routing rules for that. So what I'm going to do is I'm going to go and edit the virtual service gateway. Oh, sorry, I'm in the wrong project, I think. Oh, on the wrong user. I'm going to log in as admin here. I'm going to edit the gateway. And in the gateway, I have a routing rule that says for calls that goes to the gateway, we're going to use the subset called type spring. So I'm going to change that, and I'm going to do type vertex instead. Oh. We're going to save that. And when I've saved that, if we go back to the application and we reload the application, you're now going to see a small interactive. We are reactive here in the corner. And that illustrates and says that we are now using the Vertex version of the service. And it seems to be responding a bit faster. So let's see in a trace in Jagger where we're using the Vertex version instead. So I'm going to change this to the gateway. And I'm going to find a trace from a few seconds ago here. And here is an example where we're using the non-blocking reactive platform, Vertex here instead. And because the external calls to the inventory is happening asynchronously in a non-blocking fashion, it looks like we are making them in parallel, but we're doing them in parallel without the cost of spinning up extra threads just to make them parallel. So we are they're still taking above 100 milliseconds to execute, but we are now making them over the same time. So overall time for this call is now 150 milliseconds. Remember, it was 800 milliseconds for the blocking call. So that makes it much more efficient and using much less resources for us. So let's see what we can do in terms of the performance. What happens now if we run the same test? We're going to run exactly the same test. 10 users, 10. Maybe bring that up to. Let me bring that up so you can see it here. Siege. There we go. Same call as we did for Spring, but now for Vertex. And now we can see that not only is it responding faster, we don't have any errors, we have 100% availability, and we have a bit higher transaction rate here. Let's actually put a bit more load on this. Let's do something like 25 here. So we're gonna go to, not 250, 25 clients here. Again, we can see the time here goes up a bit. We are getting closer to 1 second, but still we have 100% availability. We have as much as 37 transactions per second now going through. So much faster and much more stable, and it's still using much less resources. We don't have any blocking issues where we have running out of threads in a thread pool, etc. And this is because of the non-blocking technology. So, by the way, both of these are runtimes that are fully supported and part of our OpenShift application runtime offerings. This is part which you can run, and we're running this on top of Kubernetes platform, and a Kubernetes platform called OpenShift from Red Hat. And this, as I mentioned, this is a distributed tracing capabilities that are called Jagger, which is part of the Istio framework, which is coming in the service mesh that is coming into to OpenShift platform sometimes next year. It's in technology preview right now. So that gives you an idea of the importance of choosing right tools for right task. there are use cases where a servlet container would be better perhaps than a reactive platform. So the point here is just that you should be able to select multiple type of runtimes, whether that's a reactive runtime, a non-reactive runtime, whether that's a JavaScript framework, or etc. It's important to be able to choose different runtimes depending on the problem and what you're trying to solve with this. So I hope that was a nice demo for you. So now we're going to go back to the presentation, and we're going to continue.
Yeah, and that basically addresses the need that customers have and already are using. In their application, they're using multiple runtimes. So that's a good segue to continue also this presentation. So let's go back to the 8 steps. So step number 5, in no particular order, is self-service on-demand infrastructure. And the idea is to allow developers to access the infrastructure when they want, without having to ask IT or wait for IT to procure that environment for them. And so this is self-service on-demand infrastructure, and what allows you to do this, a good fit for this type of environment is containers. And so it's an easy way to basically encapsulate an environment and replicate it. You can even set up a container with a best practice, an architecture that is based on the best practices of your specific corporation or company, and replicate that and have developers use that. And with containers, you have container orchestration, right? And this is basically allowing you to, it's an environment that allows you to manage the whole life cycle of the containers, and including also DEVOPS pipelines to speed up the delivery and development of applications. And as you know, all these are encapsulated within OpenShift. This is one of our products that we offer. Step number 6 is automate IT to accelerate delivery. This is an effort that should be done enterprise-wide, and things that help you accelerate delivery are, for example, automation sandboxes. These are basically environments where your developers can quickly put together ideas and develop ideas fast. It goes together with the concept of fail fast as well. Collaborative dialogue across organizations is important. Self-service catalogs that will empower users and speed delivery, as well as processes and policies for metering, monitoring, and chargeback. Step number 7 is implement CI/CD and advanced deployment techniques. This picture right here is a pictorial of what a CI/CD pipeline does. Basically, a developer will access a source repository like GitHub, for example, commit something to GitHub, and in turn that will kick off a CI/CD pipeline that will update the source code, build it, and then deploy it to a container. And then the container can be actually running on a physical machine, or it can be running on a virtual machine, private cloud, or public cloud. I put a note in here so that I don't forget that automated testing is also very important to not just accelerate the processes, but also when implementing CI/CD as well as advanced deployment techniques. With respect to advanced deployment techniques, these are 4 examples of what they are. The first one is rolling upgrades. This is the ability, the environment when you have multiple copies of a runtime environment, like in a cluster. And then what you do is you have a load balancer fronting that, and then what you do is you take off a server at a time offline, you update that, and then you bring it back online, and then you move on to the next one. So that's a rolling upgrade, right? So the user won't see a downtime. Maybe it may see a slowdown, but you will never be offline, and you update all your machines as you update each of the members of the cluster. Blue-green deployment, blue being the production workload, and then you're introducing a new updated application, for example, that would be the green deployment. And at one point in time, you're going to turn the switch to the green, and if everything starts running fine, then you can retire the blue, right? So that's another way to upgrade. Canary releases is similar to blue-green, but you're actually deploying think of the green application, but you're only routing a small number of users to it. Okay. Once you start, you realize, or you test, make sure that the canary release is working fine. Then you start incrementing the number of users until 100% of the users are basically with the Canary release, and then you retire. Basically the blue deployment is gone at that moment. And A/B testing is, thank you. A/B testing is actually a hypothesis type deployment. You want to prove a hypothesis. So let's say you have an application and you want to change the location of a button to see and see what effect that has. So you release an application with that button in another location, and then you collect data for a few days. Okay. Whereas with the other ones, it's basically happening at the moment. A/B testing is basically you're collecting data, and then let's say it's 2 weeks. Then you analyze the data to find out if the move of that button to another location actually results in positive things. If there's no positive result, then you don't move that button. That's called A/B testing. And the last step is evolve a more modular architecture. This has to do with microservice architectures as well as its alternatives. So not everyone is a Netflix. Not every corporation is an Uber. So use microservices when it makes sense to you. Just because microservices are in fashion doesn't mean that you have to jump into microservices. There are definitely benefits to using that, and apply those wherever it makes sense within your organization. There is an alternative called monolith first. So the idea here is that even if your plan is to use microservices, because microservice architectures are not easy to implement, you may, if you start with microservices, you may incur technical debts because you may not know the domain well, right? You may guess these are the things that are making good microservices. You define these areas, but then once you go into production and you're using the application, you realize that that was not quite the way you wanted to split the domain. So that's technical debt, and you have to do rewrites. So the monolith first says, even when doing microservices, start with the monolith first. And then once by doing so, you're gonna get to understand better your domain and also the bounded context. The bounded context is basically an area within the domain that is a good fit for a microservice. So, and then you can start breaking the monolith, and we covered breaking the monolith earlier. But that's the whole point, the whole concept of monolith first. And mini services are somewhere in between a microservice and a monolith. Mini services are, if you're familiar with microservices, they have to be autonomous. They cannot even share data. So a microservice, if you have has to have its own database tables, for example. You cannot share database tables across different microservices, so they have to be autonomous. A mini service is maybe, maybe you have two microservices that make sense for them to live together and share database tables. So that would be a good compromise for a mini service, right? And what else? So just to finish up some customer successes, I only have 2 minutes left. So one of our customers, ASX, is the first securities exchange that opens around the world. And they went ahead and modernized. They went from a competitive application service to EAP, to our application server. And they were able to see 60 times faster application restart speeds, for example. And now they are looking into moving that monolith into OpenShift, into containers. So it's, they're taking one step at a time. And the second use case, customer case that we have is Schiphol Amsterdam Airport. They started building modern applications using middleware components that we offer, and this talks to the application services that I was telling you about that helps you speed up your business logic, and they were able to see 50% faster development of new APIs. Now this presentation is based on a white paper that we put together. The links are provided here. There is an ebook, there is a recorded webinar, as well as a blog post. Please check that out. And the last thing that I would like to leave you with is if you go to bit.ly/mp-ebook, this is one of the runtimes that we mentioned before, MicroProfile. We use the open source project called Thorntail to implement this specification, which is a community-driven a specification for enterprise Java microservices. Please download it. It's free. It gives you lots of history and code samples on how to develop microservices using MicroProfile. Okay? And I think that's all we have. Thank you very much for attending, and we'll see you around. Any questions? No?
Okay.
All right. Thank you so much.
Thank you very much.
And 350.